Good morning, Professor. This is my final presentation, and the course is the membrane design. And my topic will focus on the hollow fiber membrane for carbon dioxide capture. And the first is why we need to capture carbon dioxide. The first is because the climate change and global warming. And because of this topic, we need to capture carbon dioxide, and they have several carbon dioxide separation technology, and they're including the absorption and distillation, absorption, and that is the membrane separation. And I will focus on the membrane separation of my introduction, and because they have several advantage of membrane separation. They have low energy consumption and simple and compact and space saving. So we use membrane to uh, do the CO2 capture. And left side is the trade-off effect. The trade-off effect will have an upper bound, and the target we need is to reach the upper bound, and the trade-off relationship of a pristine dense membrane will between permeability and selectivity. And the right hand side is the MTR standard, and it's based on the capture course and selectivity and permeance. And when we selectivity is greater than 20, the effect of higher selectivity on the cross is not significant. So increasing the permeance is the main goal. And also the gas separation have separate many gas pair like the hydrogen and uh, carbon dioxide and nitrogen, and carbon dioxide and methane. And here I will focus on the CO2 N2 separation. And the CO2 N2 separation is because the post combustion and the fuel gas will generate from the fossil fuel combustion consists of nitrogen about 85%, and the CO2 is around 15%. And how to separate this gas is based on the dynamic diameter difference and the critical temperature. And as we can see, the carbon dioxide has a smaller diameter than the nitrogen, and the most important is the critical temperature is related to the solubility. And CO2 has more high selectivity than nitrogen, so based on this mechanism we can easily to separate CO2 than nitrogen. And the next part we will focus on our research direction on hollow fiber membrane. And the first is the PDMS cutter layer modified by argon plasma process desirable hydrophilicity to facilitate the p-back coating. And the second part is the turning porphyry chemistry and PDMS cycle and viscosity reduce the PDMS intrusion. And the last part is the incorporating hydrophilic carbon quantum dots reduce PDMS intrusion. In this page, I will to introduce the structure of the hollow fiber membrane. And the first is why we choose the three-layer composite membrane, because if we only use a dense membrane, it will has lower gas flux. And when we use two-layer membrane, the thick selectivity layer will cause a high cost. So we use three-layer membrane because it can let us has thin selective layer to decrease the cost of the hollow fiber fabrication. And the first is the substrate. The substrate will provide the good mechanical property. And the gutter layer is the second layer. It can reduce the interface defects and fill the surface pore, and can prevent selective layer after coating selective layer to prevent the penetration. And the outer layer is the selective layer. It has the responsible for separation selectivity. And the next part is the hollow fiber spinning and formation. And there have several vectors will affect the uh, polymer to fabricate the hollow fiber. One is the spinner rate and the coagulant, and the air gap between the spinner rate and coagulant, and also the ball-free flow rate and top solution will also to be the factor. And here we can check our subject that the outer surface will be dense, and it can easily to get the gutter layer to coating on it. And if we have porous subjects of the outer surface, it will let the gutter layer penetrate. And also we can see the inner surface will be the porous. The porous can provide a higher gas transport. And how to modify the dense outer surface and the porous inner surface is up to the coagulant based solution. And the next part is the gutter layer, fabrication of gutter layer. Our fabrication is use the deep coating PDMS to coating on our subject. And as the graph we can see, the outer surface of the subject will have some little pores, so we need to fill the pore of the surface to make the hollow fiber becomes defect free. And how to check whether it's complete to cover the surface is we will use the e-test to check the elements, like PDMS has silicon element and PS has sulfur elements, and we can compare the peak between there to observe the phenomenon. And there have many ways to prevent the PDMS intrusion, like reduce the surface pore size of the subject, and it's up to the coagulant base. And the other is the pre-wetting to pre-wet in water, and water will be the PDMS is hydrophobic, so it can easily to coating on the hollow fiber using the pre-wetting. And the third is increase the viscosity of PDMS solution. The higher viscosity can not easily to penetrate into the subject. And the other last part is the incorporate the carbon quantum dots. And how to increase the viscosity of PDMS solution is to increase the course length time and keep the temperature at around 75 degrees Celsius. And as the steering, we can get a longer polymer chain, and a longer polymer chain will have a higher viscosity. And the last part is the selective layer. The selective layer, here I introduced the PPEX. PPEX is a common separation material and is cheaper, so they have many industry will use the PPEX to separate the carbon dioxide and the nitrogen. And because the layer PDMS is the hydrophobic and PPEX is hydrophilicity, so we need to modify the hydrophilic between both layer. And our lab is using the plasma treatment, and there have the other treatment like UV ozone and like PDA coating and some others is to modify the gutter layer surface. And we can see as the plasma treatment time increase, the PDMS will become more hydrophilicity, and increase the treatment time lead to a low permeance might be due to the formation of a dense SiO layer that can act as a barrier to gas transport. And here is my final presentation. Thank you.